All right, in this lesson, we're going to take a look at the commutator of vector fields. And where we're sitting right now is we have two ways of looking at this curvature tensor. We have this way, where we have created this mapping that takes two vector fields, operates on a third, and returns this vector field, which we see a commutator of two vector fields right here, and this certainly looks like something that's acting as a commutator as well. And then to turn this into the Riemann tensor, we write it in this form, where we are now creating an object that takes a one form, three vectors, and returns a real number. And that real number is generated by taking the dual space mapping of the one form with the vector that's formed by this mapping up here. And we went all through that in our previous lessons. And then we also figured this out in component form, where the component form is given by this tricky expression that we derive. We derived this thing twice, by the way. We derived it directly from this, using this definition, breaking this down into a coordinate basis, and then just directly calculating this. And we also developed this through an analysis of using a round-trip movement of a vector being parallel transported around a closed curve. And we separately created the components of the Riemann tensor. And we understand this is the components of this guy when this guy is cast in the coordinate basis, which means that this tensor in a certain coordinate basis can be expressed as this object right here, where this is the tensor product. This is the basis of the tensor product space, and this is the component. Okay, so we got that far, and now I want to spend a little time getting comfortable with the idea of the commutator of two vector fields, because we're going to use it a couple more times, and it'll also help us a little bit get an intuitive idea of what's going on with this curvature tensor. So let's begin. All right, so the first thing we have to kind of get a picture of is what is this commutator of two vector fields, x and y. So we have to understand x as a vector field in the space-time and y as a vector field in the space-time. So these guys are actually functions of space-time. So that little x is actually your coordinates, right? So little x you have to think of as x0, x1, x2, and x3. Sometimes you could write little x as x mu. Then you would get x, x mu, y, x mu, like that. But you understanding that this coordinate, of course, is not a tensor. I think I went through this before. The idea is that this is supposed to be some kind of capital bold face x and capital bold face y, representing the non-coordinate or the coordinate-free notation of things. But if it was cast in the coordinate system, you just write x mu partial mu, understanding that the component is a function of space-time. So this is sort of equivalent to x mu of little x partial mu, like that. And so that would be the coordinate version of this. And this guy up here, which we could bold out in this form, would equivalently be x mu x partial mu y nu x partial nu. Now what we do is we suppress the x. We suppress the little x because we understand that these guys are functions of space-time because we're dealing with vector fields. So this is the notation that is supposed to tell us that we're taking the commutator of two vector fields. Almost never anymore do we actually talk about vectors without talking about vector fields. So we could consider, however, a vector field that is constant, and in fact it could be the vector field x that's just given by the partial mu, and the vector field y that's given by partial nu. And the components of this is 1, so it's 1 partial mu, right, and 1 partial nu. And this is not, in fact, a function of space-time. Or you could say that it is a function of space-time, but it's constant on space-time. And therefore, in that case, xy would just be partial mu, partial nu. So what is this supposed to mean? Well, we know that we're dealing with vector fields in the coordinate basis, and those are operators that act on functions. So we have to always understand this in terms of some sort of test function that's out there that's unspecified and arbitrary, but it's differentiable. And so this would ultimately mean, by definition, right? By definition, this means partial nu of f minus partial nu partial mu of f. And since partial differentials like this commute, it's just a fundamental principle of multivariable calculus, this guy equals 0. So when you have these constant functions up front here, this is always going to happen. You're always going to get a 0, because even if this was, say, 7 and 100, well, 1011, say, and 7, right? These guys would both come out to be a constant here, 1011 times 7. And then you would still get this commutativity going on, and that would leave us to be 0. The problem is when x and y are actually vector fields that are functions on the space-time. When that happens, this no longer commutes, and you can no longer write this as 0. So what happens in that case? All right, so the first thing we'll do is we will rewrite this. And again, it's the same expression here, but now we understand this is a function in space-time, this is a function of space-time. And we remember that partial alpha, that notation just means a partial derivative with respect to the coordinates, right? That's what this means. 3 little lines is a quit in LaTeX. If anybody uses that, this is EQUIV, and it's meant to mean when you have 3 lines that we're just redefining things, changing things with notation, or doing something that is not mathematically material. That's the way I use it, at least. And so, so now these derivatives actually are going to matter. You can't just pull out these functions anymore. So let's literally write this down by definition. We're going to get x alpha phi alpha acting on y beta, not phi, partial beta, minus, and I'll erase this, minus y beta partial beta acting on x alpha partial alpha. And then we're going to use the chain rule. We'll get x alpha, and then we'll get, this will be the derivative with respect to x sub alpha of the function y beta, because this is where it being a function of the space-time matters, right? So that would be phi alpha y beta, and you're left over with a phi beta, and then on this side it's y beta partial beta x alpha partial alpha. And then this is written x alpha y beta single slash alpha and phi beta minus y, phi beta partial beta, y beta x alpha single slash beta partial alpha. And then what we do is we simply rename alpha to, say, rename these two alphas here to, say, sigma, and rename these two betas to alpha. So we get x sigma. This is totally just renaming. Y alpha sigma partial alpha. If you don't see why this here is identical to this, just we're relabeling and renaming things, have a look at that, because it's really important. The next step doesn't make much sense unless you understand that pretty obvious step, right? And then this would leave as y beta x alpha slash beta partial alpha. And now the two partials are the same, so we can pull them out, and we write x sigma y alpha slash sigma minus y beta x alpha slash beta, right, partial alpha. So the things we see here is that this, and then there's always a test function here, right? So there's a test function here, there's a test function. Why don't I put the test function in red? Here, here, test function here, test function here, test function here, 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 and then it comes out here. So the point is this guy here is a vector, right? Because this in here is a constant, and it's calculated at a specific point, right? There's a point where this is a function on spacetime, right? Because that's a function on spacetime, that's a function on spacetime. All of these things here, all these components are functions on spacetime. This derivative is a function on spacetime. So this is just a function of spacetime, and that is the coordinate basis. So this is another vector field, which is operating on our test function. But we kind of ignore the test function. We're only kind of interested in the vector fields themselves. So the commutator of two vector fields is another vector field, and it's not zero. Now, if these were constant functions, this term here would be zero. If the component of the vector field x was constant, that would go away. And if the component of this was constant, that would go away. And in the end, this would be zero. But that's not the case. These are generally not constants. They're functions on spacetime. So the point is the commutator of two vector fields does not generally vanish, unlike the commutator of the two coordinate basis vectors, which does generally vanish. And this actually is an important fact, because it's going to ultimately distinguish between a holonomic and a non-holonomic coordinate system, or I should say a holonomic and non-holonomic basis system, not coordinate system. And we'll discuss that in a moment. But now let's see if we can have some understanding of maybe some geometric analysis of this. And we're going to follow the work of Meissner, Thorne, and Wheeler's book Gravitation. There's no reason to diverge from that. It's not the only book that does it this way, but it's the one that I happen to have open right now. And so if you do have it, it's the analysis I'm looking at is, what page are we talking about? It looks like it's right around page 235. So we're going to begin this analysis in flat space-time, and that's almost always how these things are done. You have to understand these principles in flat space-time to generalize to curved space-time, and of course all spacetimes are locally flat. That's the whole point. We are assuming, the theory itself assumes that spacetime is a four-dimensional manifold, and it's locally Lorentzian. So when you put all that together, that means in any small enough region, you can presume that we can create a flat four-dimensional spacetime. That's an assumption of the theory. So we're going to understand this principle of the commutator in flat spacetime first. And we're going to use a vector field on flat spacetime. So let me just draw out, like, here's our coordinate system in flat spacetime. And we're going to create a vector field in this spacetime, which is telling us that at every one of these points, at every single point, we will have some function. I'll call it the first function x, and then I'm going to call the points in spacetime little x. This is a little kind of confusing, because I guess I should have like a bold x, but this little x here represents the coordinates of a point in spacetime, and this represents the vector field. The vector field is a function of the coordinates in spacetime, and that can be written in, if we cast this in the coordinate basis, it would be capital X alpha partial alpha, where we understand that capital X alpha is actually a function on spacetime. And I'm not going to write this function on spacetime. We're going to assume it's a vector field, and it is assumed to be a function of spacetime. Most general relativity textbooks do it that way. They just assume that you understand we're talking about a vector field here. So with that in mind, we're going to proceed by beginning with some point P0. And I'm following the development of Meissner, Thorne, and Wheeler It's somewhere around page, I think, 235, right? Page 235. You don't need that book to follow this, but if you want to sort of go through it from scratch, just the way I did, that's a place to start. And look, I'm not ripping off their analysis, right? This is a gazillion sources do exactly what Minor, Thorne, and Wheeler does. I just happen to have that book open right now. Well, not right now, but that's the book I'm using. Anyway, so starting at a point P0, so I'm going to use the notation in Meissner, Thorne, and Wheeler too. We are going to consider a vector field on flat spacetime, and this vector field is going to be a displacement vector field. A displacement vector field. Displacement. Which means that we're going to consider the value of the vector field at, say, point P0 will yield a vector, and the tip of that vector will be our next point, P1. Now, if the spacetime wasn't flat, you couldn't even hope to do this. This would be illogical. But because we have flat spacetime, we can kind of equate the vector space with the actual underlying 4D manifold of spacetime itself. And so we can actually have vector fields that represent literal displacements. If we're in curved spacetime, this is a little bit of a trickier proposition. We have to consider only limiting procedures and other things like that. And even in this case, you'll see in the end, we really do need a limiting procedure as well. But by treating this as flat spacetime displacement vectors, what we're saying is that everywhere in spacetime there is a displacement vector. So this one would be the displacement vector x p0. And at p1, whatever point that is, there might be another displacement vector field, which would be x p1. And that might take us to some other point. And that point, it's also will have a displacement vector at that point. But it's every other point that's out here will also have their displacement vectors that are associated with it, because every point in spacetime has a vector associated with it, because we have defined a vector field on the spacetime. So we're only going to consider right now this first one from P0 to P1. But we're going to also introduce a second vector field. And that one we're going to call y of x. And it's going to be y beta partial beta. And again, y is a function of spacetime. And likewise, there is a value of y at P0. And that lands us at a point which we'll call P2. And just at P2, there is a value of x at P2, which we'll call x of P2. And just at P1, there is a value of y at P1. And that lands us at another point, which we'll call we'll call this one here P0 to P2 to P3, and then P0 to P1 to P4, right? So because this vector field at P0 and P1 are not necessarily the same, in other words, the value of the vector field at P1 and the value of the vector field at P0 are not the same. Likewise, the value of the field of the x vector field at P0 and the x vector field at P2 are not the same. There's no reason to think that going displacing through xp0 to yp1 is going to be the same as yp0 to xp2, right? There's no reason that p4 and p3 should overlap. Now, if these vector fields were constant, which means that xp0 and xp2 were the same and yp1 and yp0 were the same, they would in fact overlap. They are, or p4 and p3 would be the same. But they're going to be off. They're going to be missing a little bit. And how much are they missing? Well, they're missing by this much, right? They're missing by that much. And so the coordinates of P4 minus the coordinates of P3 would represent the displacement from 4 to 3. And that is going to turn out to be related to the commutator of the vector fields x and y. And we're going to do that calculation right now. So I've rewritten it a little more clearly here. P0, P2, P3, where this vector here is now going to be, we're going to call that one y, y p0. Notice we're using the non-coordinate notation here. I could have written this as y beta partial beta, like that, and then I would have had to indicate at p0. So what would I have done? I probably would have done, let's see, I would have done it this way. I would have gone y beta p0 partial beta, or I could have said y beta partial beta maybe evaluated at p0. I've seen both of those notations done as usual. Then we have, this is x alpha p0 partial alpha. This is y, we'll use the other notation here, yp1. We'll just use the non-coordinate basis notation, and we'll call this one xp2. Kind of mix them up together, right? We have coordinate basis notation here and non-coordinate notation there, or coordinate-free notation there. Really bad idea to do that, but it turns out it's not ultimately super critical. We're always going to end up, in the end, going to the coordinate basis to solve this problem. So we were interested in characterizing this mismatch. Ultimately, that mismatch is going to be related to the commutator. So let's see how that works. So we start with understanding that this difference we're dealing with flat space, and these are displacement vectors. So this displacement here is equal to the coordinates of P4 minus the coordinates of P3. Wait a minute, I have this arrow pointing in the wrong direction, don't I? Let me fix that. Okay, yes, so that's the displacement vector. So now, how do we, so this now represents the coordinate, this little x of P4, that shows up in a lot of GR notation. What this means, or with the mu there, that means this is a coordinate function, and its argument is a point. So this guy returns the coordinates of that point. So this guy's got to equal something like x0, x1, x2, x3. That would be a full quadruple. What you do is, if each substitution, for example, little x0 of P4 would return x0 at P4, I suppose, it would return the zero coordinate of this point P4. So these are the coordinate functions. They're not the contravariant components of a vector. They're not that. That's a very confusing point. People try to treat this as though it's some kind of contravariant components of a vector, but it isn't. Now, in this world where space-time is flat, you can actually create displacements in coordinates as displacement vectors. You can do that, and but generally you cannot. And so you always have to remember this is not to be treated as a tensor index or as a contravariant, the components of a vector, or the contravariant components of a vector index. All right, so our next step, we'll take this first one, P4, and we'll blow it up. P4 is going to be this difference is going to be x at P0 plus y at P1, and this guy here is going to be let's see, y of P0 plus x at P2. And we rearrange this a little bit. So we combine things in where we put the y's together and the x's together, and we end up with y of P1 minus y of P0 minus x of P2 minus x of P0, right? So we're just rearranging those two differences. And now we have the formula for this difference here in terms of the vector field, right? So this is the coordinates of these points. We're now in terms of the vector field. I guess we're kind of assuming that P0 is sort of the origin of things, because we're only interested in the displacement vector. So if we treat this as the origin, so there's no coordinates there, then ultimately this ends up being just the displacements from P0. Now, what makes this, the part of this that's a bit artful and important is that this answer, the answer for what that difference is, and we have to get used to this concept because it shows up a lot whenever you're dealing with these kind of round trip pictures, whether it's the commutator or the curvature tensor or anything that involves these round trips, or is that we want to know what this displacement is given these two vector fields, but we want to do it entirely in terms of things that are local to P0. So anytime you see a P1 or a P2 where you're evaluating the value of the vector field at P2, we don't want that. We want only through knowing facts about the vector field at P0, and yet it can reach out there 2 steps away and still tell us what that displacement is, just by looking at facts that are local to this point. So clearly that's going to be an approximation of sorts, but that is our next step, is to really get rid of these arguments P2 and P1 in favor of everything's argument has to be only P0. So let's start with this one right here, the vector field at P1, this vector here. How do we estimate that vector based on only information from P0? And this is the formula we're going to use. The value of the vector field at P1, which I'm now writing as y alpha P1 partial alpha, is going to equal, we're going to do a linear Taylor expansion. We're going to say this vector field value at P1 is equal to the vector field value at P0, which happens to be this thing, which would be this vector, plus the regular derivative of the vector field with an increment in the in the x field's direction, right? Because this is the small increment in coordinates from P0 to P1. So we take that increment and we multiply it by the derivative. And this thing is the first order estimate for the value of the y vector field at P1. And of course it's a vector, so we have the partial alpha that just sort of flows out through the back of this thing. And so now everything is local to P0, but we need to know the derivative of the vector field. And since it's flat spacetime, we don't need a covariant derivative, it's just a regular derivative. And this represents really the small interval between P0 and P1, which is given by definition the x vector field. So it's the derivative times the small interval, and that represents the change in this vector field in flat space. And so that's how we're going to get rid of the P1 from yp1. And we're going to do the same thing for xp2. And here we have that worked out. The vector field at P2, this guy right here, its estimate is its value at P0, which is this guy right here, local to P0, so that's important. And then its derivative and the increment that, its derivative and then the increment is by definition the y vector field, and that's the first order correction, and it gives us this value. So now we've eliminated xp2 in favor of things entirely local at P0. And once we have that, now in order to calculate these two terms, we just make these subtractions. But this part is already local to y, and this part is already local to x. So subtracting xp0 from xp2 is just getting rid of this term, right? Because that is xp0. So if we throw down a minus x gamma p0 partial gamma, then this term is going to just cancel with that. It's only going to leave that first order derivative term. Likewise up here, when you subtract yp0, that term will go away and you'll be left with that. And ultimately what you're left with is this guy right here, which is this term here and this term here. Notice I've dropped the p0s now because everything is understood to be local at p0. So this function here, the first derivative of the y vector field, is evaluated at P0. this component of x is evaluated at p0. I didn't even write that in there. I probably should have, right? There should be a p0 here and a p0 here. It's just sort of implied. But those are functions of spacetime, so it really needs to be understood. And now we just take this difference, and this difference will represent this difference, which is that mismatch between using these displacements in two different ways around this circle. So when we look at this, we've got to kind of unpeel this thing in our notational system. And the way to do that is, first we understand that these are numbers, right? These are just regular real functions. So they commute. Whether you put the y delta here or here doesn't matter. I could have written this as minus y delta x gamma partial delta partial gamma. That's fine. That you want to keep this at the end because that's an operator waiting for some kind of function to operate on. But these two guys are just functions, so you can swap them out. And then you can write that as y delta partial x delta of x gamma, right? And remember, since x gamma is a function on spacetime, that derivative makes perfect sense. Just throwing in the missing note. I guess the hidden notation is this. This is a function on the spacetime, right? That's what's missing. And then partial gamma. But now look at this guy. This is actually, the next step is to write it as y delta partial delta, right? Because d by dx delta, the notation is just partial delta, right? X gamma partial gamma, and this is y, and this is x, right? In the coordinate free notation, this is y and this is x. Likewise, if you break this down here, you're going to end up with x, y. So you're going to get, in the end, x, y minus y, x, which, by definition, is the commutator of x and y. So to first order, to the sense that the approximation of this vector field here, right, is to first order given by this expression, that means that the displacement, this displacement here, is given by this commutator between the two vector fields, x and y. Now in the next lesson, we'll do this for curved spacetime, which I'm going to use a diagram like this to describe. But it is the same idea. However, we can no longer really rely on the coordinates of P4 and P3, the difference in the coordinates to be the relevant fact, because we can't really treat these guys like displacement vectors anymore. The reason we were able to get away with it back here was because in flat spacetime we can make assumptions that the tangent space and the real underlying space are the same place. There is no flat spacetime is saying that there's no curvature, that the connection is such that parallel transport means exactly what we think it means. And so we can talk about displacement vectors from points in spacetime to other points in spacetime, and those coordinates of those points we can just simply add using these kinds of concepts, using the fact that, well, I guess when we said that P4 was equal to this vector plus this vector, we can do that in flat spacetime. But in curved spacetime, we have to think a little bit more carefully. And what we'll do is we'll take the vector field and we'll set up the congruence of curves to which the vector field is always tangent. And then we'll start working a little bit with these curves. In the end, it actually looks very similar, but we have to just be a little bit more cautious, and it's giving us a little more insight, too, in regarding the nature of curved spacetime. But ultimately, in the end, we're going to discover that a significant distinction between P4 and P3 is related to the commutator of these two vector fields. We're going to basically prove the same fact, but we're going to look at it in the context of curved spacetime. But even if all you remembered was this, you don't really need that other analysis so much, because we do know that in our model of space-time, if you keep this region small enough, then space-time always appears flat, right? There's a way of staying so close to P0 that the curvature of space-time becomes less and less significant. And it gets to the point where this statement, this final statement in the end, you can rely on this model, even in curved space-time, as long as you could transfer to a set of coordinates where space-time is flat to first order at P0, or you could keep this guy just so small that, because remember, that's the whole point of being a manifold. Our assumption is that space-time is a 4D manifold, which means it looks like well, I shouldn't write R4. It's four-dimensional Lorentzian everywhere at a small enough scale. And so this will be true to first order in total flat space-time everywhere, no matter how big this is. But even in curved space-time, even in seriously curved space-time, near black holes or something, you can still find a small enough element where this commutator is a very strong predictor of this difference in coordinates, as long as you're on a small enough scale. But the next lesson we'll talk a little bit more about it in curved space-time, and we'll try to start seeing its relationship to something called holonomic and non-holonomic coordinates. Okay, so I'll see you next time.